All right. Hey, everybody. It's been a while. Did you miss me? Just say yes. We'll all feel better that way. Did you miss me? Yeah. Yeah. So, sorry about Tuesday. Sick again. Thankfully, that was a fast one. So, life is better. Until this morning. Yeah, no. I'm just going to complain a little bit. Is that okay? You're welcome to complain as well. Everything's going along fine until all of a sudden my back/neck decided to kind of stop working. You know that feeling where just out of the blue it's like, so I'm feeling kind of robotic now because I can't seem to look left, right, or down very well. So there's a whole lot of like, who's behind me? How you doing? You know, that kind of stuff. So hopefully that goes away soon because ouch, it doesn't feel so wonderful back there. What else? I sent out an email. Homework pushed back to Saturday night since I wasn't here Tuesday, just to give you a chance to ask questions, etc. And our second midterm is pushed back 2 class sessions from what it was on the syllabus. So instead of Thursday the 8th, I guess, it's Thursday the 15th of November.
Didn't we just, it feels like we just had a first midterm.
It really does, but alas, these things come quick at this point. And even then, that's still, what is that, 3 weeks from today, I think? So we've still got a good bit of time. It's not that fast.
I think it's because we're only in classes 2 days a week.
Yeah. Don't you wish we had this 3 instead of 2? No. But the classes would be shorter, you know. I kind of like the 3 days a week thing because it feels like about 50 minutes is about all any of us can handle. Because you'll notice at about the 50-minute mark, like all of you are kind of, yeah, and maybe I'm kind of like, ugh, and then, you know, we all kind of get together for the last little bit, but 50 minutes is just a better class all around. You just have to see me more often. Which is good or bad, I don't know. All right. So since it's been a little while, we were talking about circular motion. Thankfully, the last several slides of this chapter offer up a pretty good review and allow us to work a lot of sort of mini problems as opposed to just like quick multiple choice things. So the first one of these is relatively fast. Hold on a second here. Let me see what we've got coming. And then some of the later ones are a bit involved. So take a read of this one and let me know what you think. There's really only one answer that almost has anything to do with physics. Yeah. 2. The other ones sound too much like excuses, right? It's like you're driving your dad's car and you ended up skidding. So what are you going to do? It's like, it was a deer. No, that's not it. Dad, your car is too heavy. That sounds like a really ridiculous excuse.
What is skidding? Like, is it?
Yeah. What we're saying here is that it is essentially leaving the curve. So you might think of this as going straight. In other words, it's time for the ditch. Okay, so we're essentially sliding sideways out of the curve is basically what's happening. So the only thing that allows you to continue to turn is friction. It's not how strong the engine is or how heavy the car is or whether there's a deer in the way. If there's friction on the road that points to the middle of the circle or the middle of the curve, it allows you to continue traveling in that curve, all right? Here we have a circular track, or it says a circular tube that's lying flat on a tabletop, and we're going to shoot a ping pong ball into it and decide what happens when it leaves the tube. 1, 2, 3, 4, or 5. Any other votes out there? Looking for fingers. Oh, which one is it? Yeah, it should be number 2. Number 2? Why? Because there's nothing forcing it to travel in a circle anymore. The only thing that's making it move in a circle is the fact that there's this tube that exerts some sort of force on it and makes it bend around. As soon as I remove that, it's going to continue doing exactly what it was doing at the instant I took it away, which is traveling with a straight velocity, and it's just going to keep going in that direction with nothing to make it turn any direction at all, okay? So it's just going to keep going straight and follow number 2, which brings us to this one, which is going to take a good bit more work, and we're just going to work it together, okay? 2 equal mass rocks tied to strings are whirled in horizontal circles. So despite this, imagine this is flat. We're essentially taking 2 and just like swinging around like this so that the rocks are traveling in circles. And we're going to say that whatever we're using to twirl that with, the ropes are staying horizontal as well. So that's a little hard to maybe pull off, but maybe if you imagine like I hold the string here and go like that, you can imagine the rock goes around in a circle like this, okay? So the radius of one circle, the second one there, is twice that of circle 1, okay? So in one case, we've got more string than in the other case. The period of motion is the same for both. By period of motion, what we mean is the time to go around the circle. So despite one of them having to clearly go farther because the radius is bigger, they take the exact same amount of time to travel around the circle, all right? So let's compare a couple of different things. First of all, the circumference of a circle. What's that equation? 2 pi r. So if circle 2 has twice the radius, that means it also has twice the circumference, okay? So circle 2 has 2 times the circumference. So in other words, the rock has to go twice as far in the same amount of time. Okay? So for circle 2, the rock travels twice the distance in the same time. What does that tell us about how fast it's moving compared to rock 1? It's definitely moving faster. Exactly how faster? Twice, right? It's traveling twice as fast if it covers twice the distance in the same amount of time. So that means it's moving 2 times the velocity. Okay? So we can sort of deduce all that from the reading of the problem, which I know is a good bit, without even getting to circular motion or dealing with equations or any of that stuff at all. At this point, we can break out our new equation. The sum of the forces in the c direction equals mass times the acceleration in the c direction. And you remember the c direction always points to the middle of the circular motion. So in both of these cases over at the right, well, the middle of the circular motion is right in the middle of the circle. So that's positive c, or directly there is positive c. And no matter where the rock is in the circle, the c direction is always toward the middle. Okay? Now, what is the one force that's acting in the c direction?
Tension.
Tension. That's it. We know that there's going to be, well, gravity, but it's pointing maybe into the screen. Okay? It's perpendicular to the circle. So the only force that I have is tension force, which points to the center of the circle. So Ft points to the center of the circle in both cases. So if we go back to our equation, I have Ft equals mv squared over r. And they want us to find how the tension compares for both of these cases. How the tension compares. This is the only force that I have in the c direction, F, and the acceleration in the c direction is v squared over r, okay? So we just determined for circle 2, it's traveling twice as fast, okay? So that's part of it. For circle 2, we have 2v, which is going to get squared, so I have 4v squared. But don't forget, it also has twice the radius, okay? A little bit of a trick there. So there's a factor of 4 that's happening in the numerator and a factor of 2 that's happening in the denominator. So the overall factor is that the tension is twice as large for circle 2. So you could say that T2 is double that of T1, okay? And I think if you just imagine like twirling rocks around in a circle, the one that's moving faster, even at a bigger radius, you can imagine it's going to be a little harder to hold on to, right? There's going to be more tension in that string. That's a tough one. Let's stop for a second. Look back through it. Is there anything that's confusing you or bothering you?
Why does the length affect the tension? It seems like since the ball weighs the same, wouldn't the tension be the same?
Why does the length affect the tension? You can imagine that the radius of a circle it's about how tight the object has to move to turn in that circle. Okay, so there's more centripetal acceleration for a smaller radius circle because I have to change the direction faster. So with a bigger circle, like it's just sort of barely changing from one instant to another, but with a small circle, it's changing really rapidly. Okay, so higher radius, lower acceleration, and vice versa. Next problem. Okay, actually I'm gonna skip this one. This is about a barrel of fun. No, it's not a barrel of fun. In fact, it just serves to confuse people, okay? There's nothing instructive in that problem, so we're not gonna worry about it. Instead, we're gonna move on to a Ferris wheel. A Ferris wheel moving in a vertical circle. So a vertical circle, yay. When the Ferris wheel is at rest, the normal force exerted by your seat is equal to your weight. So you're just sitting there in your seat. It's like, oh, my seat's holding me. It's equal to my weight, okay? If you imagine now this seat that you're in moving around in a circle, let's get rid of that so I can actually draw a curved line. And let's look at just the forces on you as you move in that circle, okay? So here we are at the top of the Ferris wheel, and you're just going around in a circle like this, okay? What forces are acting on you there at the top? Name one. You're sitting in your seat. Gravity, normal. I heard both of those. So gravity points down and normal points up. That's specifically not the force on the seat, that's the force on you sitting in the seat, okay? Is there anything else? Sitting in a seat. Not really, right? You're just sitting in a seat. It's supporting you and your gravity is down. When you're at the top, which way is the C direction? The center of the circle is down here, right? So the C direction is straight down, plus C. So to solve this problem, let's write out the sum of the forces in the C direction. The gravitational force is pointing in the positive direction and the normal force is pointing in the negative direction. So I've got F sub G minus Fn equals mv squared over r. And they want us to find how the normal force changes when you're at the top of the Ferris wheel. Is it more than your weight, the same as your weight, or less than your weight? This equation will tell us because I can solve it for the normal force. And I get Fg minus mv squared over r. The normal force is not equal to your weight. It's equal to your weight minus this other term. It's less than your weight when you're at the top, okay? Because this term is being subtracted. Think about traveling over the top of any circle, okay? Maybe I'm just driving down the road, okay? And I reach a place where it's like, ooh, and you have to go over like a bump. Basically, you're traveling in circular motion there for a bit. When you're at the top, what do you feel in your seat? Right? You feel just a little bit out of your seat, maybe a little bit lighter than normal. That's because the normal force is no longer equal to your weight. It's a little bit less. Okay? Same thing happens here. Got it? Got it? Yeah. Yeah.
Is it always the same on any part of the Ferris wheel?
It's different on different parts of the Ferris wheel. The reason being because you can imagine if I'm down at the bottom, well, now the normal force points to the center of the circle, and the gravitational force is in the negative direction. At the bottom of the circle, the signs get flipped, and you feel like you weigh more. The normal force is greater than your weight.
So the force arrows stay the same throughout, like you
Yeah.
your Ferris wheel, and it's just relative to the ground or to the center of the circle of the ground.
Yes. Yep. The direction of those vectors stay the same. It's the c direction that's changing as you go around the circle. Okay? Let's try more with this creature once again. Oh, that was really no way to leave you guys for a week. Yeah? Nightmares? I have been. That's why I couldn't come back. That's all I've been thinking about is this diagram. So here we have a skier that's going over a small round hill. Hill? What am I saying? I can't even pronounce words now. A small circular hill. Okay? So we're looking here at the top. The forces acting on the skier there at the top. Well, they're the same as in the last problem, right? We've got a normal force that points straight up, and we've got a gravitational force that points straight down, and the c direction is also straight down. So you might expect we're going to get something kind of similar. They're just asking a different question this time. If I write out the sum of the forces in the c direction, well, we have the gravitational force minus the normal force equals MAC. But notice the wording of this question. It disagrees with the way that I taught this class. It says there has to be a centripetal force. No, just there has to be forces in the c direction, okay, not a specific centripetal force. Instead, this is asking what is the sum of the forces in the c direction. That's what's known as centripetal force more colloquially. So over here, all of these are sum in the c direction, sum in the c direction. You can see that one of them matches what we have here, that the sum of forces in the c direction is the gravitational force minus the normal force. And that is answer 2. Terminology looks a little bit different. The symbols are different. But only one of those matches what we get in our equation. Okay? It's not asking about a specific force. It's asking about everything on the left side of our equation. Okay? I'll wait a second again. Anybody? Anything? Yeah?
So is FG positive because C direction is positive?
Yep. Yep. FG is positive because it's pointing in the positive C direction. Okay? Yes?
How do you know it's the gravity minus the normal force and not the other way around?
It's because positive C is always toward the center of the circle. Always, 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 always. Okay? And we're specifically looking when I'm at the top of the circle. If I look at the bottom, when I was here, the C direction would point up. If I was over here on the side somewhere, it would point to the right. The C direction is what changes. Okay? If you get the C direction correct, it'll define the sign of your other forces. I think there's one more. Yep, one more of these. And again, this one, there has to be a centripetal force. Get rid of that. Instead, we're finding the sum of the forces in the C direction when the ball is at the top of the motion. The top of the motion. And this time, instead of a horizontal circle, we're swinging it vertically. So imagine just a rope and a ball that's going around like that. Okay? So here at the top, again, the C direction points straight down. What forces are acting on the ball at that point?
Same thing as the Ferris wheel.
Partially.
There's no normal force.
There's no normal force this time because there's no C. There is a gravitational force. and what else?
Tension.
Tension. They both point in the same direction this time. Two forces both pointing to the center of the circle, okay? I don't think we've had that before, where two of them point in the same direction. There's no reason why we can't. We could have multiple forces that point in the same direction. So that means when I write out the equation, we've got Ft and Fg, both pointing in the c direction. So when I look up at my possible answers, that is the one we're looking for. It's the sum of the gravitational force and the tension force. Okay? Questions on that one? Yes, ma'am.
I think I'm supposed to know this, but why does tension force point towards the
It points along the rope in a pulling direction. So you can imagine the hand at all points is sort of pulling the ball inward to keep it from flying out. Okay. Anyone else? That is the end of chapter 6. Ta-da! Yay! Cheer! Yay! End of chapter 6. Yay! That's not a cheer. I don't know what that was. I'll take all that back. So, let's jump over to a new slide, chapter 7. And let me point out where we stand on things. Okay? Just to give you a little summary of what we've done so far and where we're going. So you might remember that we did a whole lot of stuff with motion. We did like 1D and 2D motion, and we had our kinematics things. We did all of that stuff, okay? We had our 4 kinematic equations. We used them in 2 dimensions, and that was kind of the extent of all of that stuff we did. Second, we dealt with forces. So we learned about Newton's laws, and we did free body diagrams, and then we did like advanced force problems, which included things like what we just did with circles and things like multiple objects all attached, okay? Even though it feels like this class has been going on for quite some time, which it has, that's what we've done so far. And it seems like looking at that list that we haven't done a whole lot, but we've done a lot. There's a lot that's buried in there, but to give you kind of the I don't know, the 50,000 foot view looking down, like that's where we stand. We did motion, we did forces, okay? At this point, we're making a bit of a hard break, a little bit of a hard break when we get to the third topic in this entire semester, and it doesn't mean we're not going to use 1 and 2. You'll see even today, we're going to draw forces. We're going to talk about forces. There will be free body diagrams. All this stuff fits into what we're about to learn about, but it's kind of like we're going to be looking at the same things from a new perspective. It's like another side of the same coin. We're going to be able to solve some of the same problems with new tools, okay? And this whole section is about work and energy. You will find, we probably won't get to it today, but next Tuesday we'll work a problem, and you'll be like, oh, that looks like a kinematics problem. I know how to solve that. And you'll like write out the variables, and you'll be like, it's in free fall, and you'll know what gravity is and the stuff, and you'll know which equation to use, and you can find the answer. But I will work the problem for you a completely different way, and you'll be like, well, that was easier. And then you will throw things at me. Okay, because you'll be like, why didn't you just teach us the easier way? Well, it's easier sometimes. Sometimes this way would be harder. Much like, oh, I don't know. Let's see. If I draw 2 things that look like this, let me see what everybody thinks of. So maybe on this one we have something that looks kind of like this. And on this one we have something that looks like this. What did I just draw? You're talking a negative and a positive. I would agree with that. Does it make you think of anything else? What are you saying? Ions? Think mechanical. I love how all of you are completely off in a very different place than I'm thinking.
on and off.
Screws.
Ooh, yeah, screws, right? The tops of screws. Yeah, no one's ever going to get that, right? But see, finally we got there. Now, two different types of screws. They require two different types of tools, right? There's the flathead screw, with which you use a flathead screwdriver. And then there's the Phillips head screw, where you use a Phillips screwdriver. Now, I could take the tool for the left one and probably use it with the right one and get the job done. But if I want my work to be a little easier, I use the tool that matches the head of the screw, right? That's what this future stuff is going to kind of be like. You're going to look at the problem and be like, I could get at it two different ways. I've got different tools I could use. One of them will be harder, one of them will be easier, and it's not like it's always that the one side is easier than the other. One of the tools will work a little bit better for the problem that you have, and you can save yourself some work by picking the right tool. How will you pick the right tool? Ideally, it would be as easy as just being like, well, here's the screw and here's the tool. Which one matches? Like, put the square into the square hole kind of thing. But it'll take a little bit more intuition, but I hope once we get there, you'll start to kind of develop that a little bit, okay? So let me get rid of these screws or ions or electrons and protons or whatever else that you thought it was, but that's fine. I completely understand why you all went down that road. And let's talk about some new tools that we can use. The first one being something known as work. And it really seems depressing to have a lecture on work. You know? It's like, isn't it hard enough to just deal with physics? Now we have to deal with physics work. Okay? It's just kind of sad in every way. Notice this definition. The transfer of something called energy by means of something that we already know about called a force. The transfer of energy by a force. At this point, you don't need to know anything about what energy is other than sort of your own perception of what energy is, okay? If you were to, I don't know, put a student in a chair here and say, go to sleep, student. And then the student's like, and then right next to the student, like maybe there's like a 3-year-old child that's all like, the whole time. You would look at these two creatures and be like, the child has more energy, right? That's relatively straightforward. Now, the child could transfer some energy, right? Maybe the child is like, is that what children sound like? I don't know. Apparently I have a weird conception of children. And the child could apply a force to the sleeping person, and the sleeping person might go from a state of no motion to like, or maybe even fall out of the chair. I don't know. Well, that's a transfer of energy by a force. The one object had a bunch of energy and gave some energy to the other object by applying a force, just by shoving. That's all you need to know about energy at this point. Just think of energy as something that's literally more energetic, something that's more full of energy, more full of life, more full of motion, okay? If you can just hold on to that idea of energy, we can get through like the first half of this chapter before we talk about energy a little bit more, okay? We good with that? Energy? Yes? Okay? And you're now starting to wonder what kind of interactions I've had with children over the years that made me describe them in such a way. I don't know what that is. Don't worry about it. Okay? So, a few different things. First of all, notice it says here, by a force. We're going to have to be a little careful about which one. Often, an object has more than one force acting on it. So we might say, well, how much work is that force doing? Maybe it's the gravitational force, or the tension force, or the friction force, or the spring force. And then we might have a separate question, same setup, how much work is that force doing? We have to be careful and be specific about which force we're talking about, okay? Each individual force that's acting on an object may or may not be doing work, and very well may be doing different amounts of work, okay? So be a little bit careful and specific about which force you're talking about, and read the problem carefully to see which force it's describing. A couple of side notes I should put here at the bottom. First of all, work is a scalar. And this should be maybe cheered with great happiness because vectors take more work. Work. Yeah, different version of work in that sentence, okay? Scalars, you can just add and subtract. Just regular old math like you've been doing since you were the child going, you know, just adding 1 and 1 together. So you don't have to worry about components or vector addition or any of that crazy stuff or directions. It's just like there's an amount of work, here's an amount of work, put them together. So that's kind of beautiful, all right? You might also be thinking like, oh, well, this sounds like a better tool. This is an easier tool to use. So yes, if given the opportunity, this might be the preferable tool because the math is simpler. So if it's possible to use it, this is a good route to go. Also, let's see, I should give you the unit. The unit of work is the joule. The unit is the joule. We're not talking about vaping. I heard the laughs. I was like, why laugh about joule? Joule. Ah, joule. Okay, that's where else I've heard this word. Okay, just to give you some idea, 1 joule of work is approximately the amount to lift an apple 1 meter. That is terribly approximate. I just want to give you a feel for the unit. Okay? 1 joule of work is about how much effort is required to take an apple and just lift it 1 meter against gravity. Okay? So when we get to problems and it's like, oh, this required 2,000 joules of work, you should go back to this, right, and envision 2,000 apples being lifted 1 meter. And like, okay, that was a lot of work. It doesn't really feel like a lot of work. It's just going to take a while. Although if you tried to lift 2,000 at one time, that sounds like a good bit to deal with, okay? 1 joule is approximately the amount to lift an apple 1 meter. Let me go back up to the scalar thing, and I want to point out something. This might confuse because back in one-dimensional motion, we use positives and negatives to indicate direction. Well, scalars can have positives and negatives too. They just don't indicate direction. Just like on a number line, I can have positives and negative magnitudes, okay? So we are going to have positive work when energy is given to an object, and negative work when energy is taken from an object. Positive work is when energy is given to an object. Negative work is when energy is taken from an object. So the little kid running around applying a force to the person, that kid did positive work on the person who was sleeping, okay? If, on the other hand, the person sleeping is sitting here like, why won't the kid be quiet? And the kid's all shaking around over here, and they go and grab the kid and make them be still, right? In that case, they took energy out of the kid by applying a force. Well, that would be negative work, okay? Nothing terribly difficult there, I don't think. So let's do some calculations. Yes.
Okay, so, like when I've heard of like work in the past, like in physics, it's always described in terms of like physical contact. So friction, lifting things, stuff like that.
Yeah.
Do you have to have physical contact to have work?
No. Gravity can do work, and gravity doesn't have to touch you. Okay? Yeah, gravity's weird. Gravity's weird. Magnets and electric things can do work too without touch. Okay? Although I'm going to describe much of what we're about to do in terms of physical contact. All right? So, let's start on the simple end of things. And I'm going to sort of give you the basic equation at the start in a basic example to give you a feel for what I mean by work. And we're going to sort of expand it out into a more general equation that'll work in more circumstances. Okay, so we're going to start with a constant force. Whatever force is being applied to the object stays exactly the same the entire time, right? And then we're going to say that that constant force is in the direction of the displacement of the object. Constant force in the direction of the displacement of the object. So I need a diagram. Here's the ground, here's a box, here's a force, and let's say that the object moves from here over to here. A constant force that's in the direction of the displacement of the object. So I push the object along the ground and it gets displaced. You might imagine if it starts out not moving and my force gives it energy such that it is now moving, I've done positive work on that box. The equation we can use for this is simply this. Work is equal to that force times the displacement. Force times displacement. And we're specifically talking about this one force. We're not talking about gravity. We're not talking about the normal force. We're talking about how much work is being done by that one pushing force. Okay? Force times displacement. And yes, just looking at that equation, notice force is in the same direction that the object is moving. This does give us positive work. I'm transferring energy into the object and making it move. Okay? Let's look at a second case. And let's say perhaps that the object is already moving. So maybe it's already moving this direction, which means that, yes, it's going to have a displacement in this direction. But let's say that this time I'm attempting to stop the object. So I apply a force against it. So it's already moving this direction, so it's going to still have some displacement in this direction as I try to stop it. If you're like, well, what are you, weak? Why don't you just stop it? Well, let's pretend it doesn't work that way. Let's say that more like this is an oncoming train and I'm a superhero, right? The superhero never just says, train, stop, and it just stops in place. It's always like a sliding backwards along the track, right? Like all the way to the edge, probably, and eventually, they bring the train to rest. That's essentially what's happening here. It's already moving. It's going to keep moving, but I'm going to apply a force and slow it down, okay? In this particular case, well, notice the force is in the opposite direction from the displacement. We can still use F delta X. We just have to keep in mind that this is going to be a negative amount of work because I'm taking energy out of the object. I'm going to show you here in a second where that negative is going to come from. This slide is merely dealing with the most basic of cases in an effort to get you to understand what we mean by work. Force times displacement. Okay? Questions? Thoughts? Complaints? Anything? Lunchtime? Yeah, I feel you. It is lunchtime. We should just have delivery scheduled for, about this time, every class. Food just shows up. We could say the delivery point is that window. Someone could just wander in and bring us food. I would eat it.
Amazon doing something.
Amazon? No? What do we want? Could we agree on a meal? Pizza? Pizza usually works, but even then, there's going to be 10% are like, I don't want it. Pizza. And then we have to decide on type of pizza. We'd never get anywhere. It'd be sad. Bring your own lunch. It's not going to have to be. So let's step this up just a little bit. Let's say that now we have the same constant force, but we're going to apply it at an angle to the displacement of the object. This better approximates what might happen in the real world. Maybe I want to move the box along the ground in some direction, but instead of having to bend all the way over and apply a force that's parallel to the ground, I'm probably just gonna stay standing and just push the object kind of like this, right? Just because maybe I don't wanna have to bend over at all. So maybe I apply the force this direction. Now notice there is an angle here between the direction of the force and the direction of the displacement. The direction of the displacement is perfectly horizontal and the force is not. If this is the case, we have this equation. The work done by that force is force times displacement times the cosine of the angle between those two vectors. So the cosine of the angle between the two vectors. Let's think about this a little bit. Bless you. There are issues. We should close the windows. Things are getting in. What happens if theta is 0?
Cosine is 1.
If I plug in 0, cosine would become 1, and then I just have that equation, right? It simplifies back to the more simple case. In the situation where instead of applying a force at an angle, I do tilt the force all the way down and apply it parallel to the direction that the object's moving, okay? So this is a better equation because it handles that force. I can deal with an angle. If the angle goes to 0, I get the first case, the more simple case. What if theta is 90? Yeah, if theta is 90, the cosine of 90 is 0, I get no work. That's the case where the force is pushing straight down the box while the box is moving sideways. This would be like a friend who's not very helpful, okay? Let's say maybe I need to move a big box, and I'm like, hey, I'm gonna move this box. And I start pushing on it sideways, and your friend's like, I wanna help. And they come up, and while you're pushing it sideways, they just push down the whole time, right? What kind of sad friend is that? Even without knowing anything about this equation, you're like, you're not helping, dude. Like, what's the problem here? In fact, you're making it worse because you're increasing the normal force, which increases the friction, and everything is terrible, right? Pushing down. That person is doing no work, and this equation tells us they're doing no work, okay? So the next time you have a friend who does something like that, be all like, F delta X cosine theta, what's the problem? No one's going to do that. That's fine, okay? So this handles kind of both cases. Now, I want to describe what it's actually telling us, and we're not going to do this part B here because it may just confuse a little more, okay? So we could describe that equation as being the multiplication of the displacement and a component of the force that's along the direction of the displacement. In other words, if I go back up to the same diagram, I could break this force up into components, one that is parallel to the ground and one that is down, one that's perpendicular to the ground. We just said that a pushing down force, that doesn't do any work. And that's true here as well. This pushing down component isn't doing us any good. It's only the component that's in the direction of the displacement that's actually contributing to the displacement, okay? So this side is going to be F cosine theta. So the component of F in the direction of the displacement, F cosine theta, and we're multiplying that by the displacement delta X. Look at what we have there. Well, that's the same equation, right? Delta X, we just move things around a little bit, but it's the exact same thing as what we had above, okay? It's the displacement times the component of the force that's in the direction of the displacement, okay? So you might imagine as we take the force and put it at different angles, if I tilt it down more and make theta smaller, I'm essentially getting rid of the vertical component and making the horizontal component bigger. If I start to tilt it up, I'm making the component that's actually doing the work smaller, and I'm making the one that's useless bigger, okay? So you can start to see how the components interact with the displacement, and the more of the force I can get in the direction of the displacement, the more work I'm getting out of that force, all right? Let's stop there and see who has questions. This isn't too bad, right, compared to some of the things we've been doing lately? It feels like maybe a step in a different direction, but also it's not nearly as hard as some of the things that we've been doing. It may just ask you to use your brain slightly differently, okay? So F times delta X cosine theta. Mathematically, does it remind you of anything? Think back earlier in this class. Think to maybe one of your math classes. Does it look like something? What if instead of the F and the delta X, I just wrote AB cosine theta? Does that remind you of something? It's a dot product, okay? We talked earlier on about like two different ways to multiply vectors. That's essentially what we're doing here. We're using a vector multiplication known as the dot product, and we could say, in general, the work is the dot product of the force and displacement vectors. F dot delta X is F delta X cosine theta. Back in your notes and see that that's true. You don't necessarily need to know that connection. I just want to point out that that piece of math isn't totally useless. It's just a more convenient way to express this, okay? F dot delta X. Let's see, is there anything else that I wanted to say about this slide? Oh, there is. What if theta is bigger than 90? What's the cosine of something larger than 90? It's negative, right? So in other words, if I take this same force up here, and instead of making it go from 0 up to, we know 90 is useless, and start to tilt it the other direction, such that it's working against the displacement, then this equation will automatically give me a negative out of the cosine. I don't need to think about whether it's doing positive or negative work. That equation will just do it for me, okay? The cosine will give me a negative if I'm doing negative work, all right? So this is really where it's at. This equation is what you want to be using. It handles positive, negative work. It handles all angles, even if they're 0, okay? You like that equation, yes?
So is it almost like pushing against the box on the other side? So if you're pushing the box this way.
Yeah, so if it's like moving and I'm pushing back the other way even a little bit, I'm doing negative work and attempting to slow it down. I'm taking energy out of it. Okay, let's move on. So, is it possible to do work on an object that has no displacement, that remains at rest? If it remains at rest, then delta x is equal to 0. If delta x is 0, then, well, the work is 0. So, no, that's depressing. It needs to move if it's actually work. So, if I sit at a computer all day and type, did I do work? Yeah, I did, but you know, it's a different kind of work. Something's moving in the head somewhere. I guess I am moving my fingers up and down a little bit, but it doesn't seem like a
Why
lot.
does that terminology work? I mean,
Why?
It just seems confusing.
I would agree that a different term might, it's just that the word is in the mainstream in a way that's different than what we mean in physics. What should we call it? We could just adopt something new, and then maybe physics classes in the future will use it, and there will be less confusion. No one wants to suggest a name? No? Okay. Fine, I guess it has to be work then. It's too bad. I like to work or not to work. Not to work, but no, sadly we can't do that. A box is being pulled across a rough floor at constant speed. What can you say about the work done by friction? I'm going to go ahead and draw out the free body diagram with everything that's there, but this is focusing on only one force. And maybe we say that the displacement is this way. Is friction doing no work, positive or negative work? doing negative work, right? It's opposite to the direction of displacement. In fact, you could say that theta here is 180. So the cosine of 180 is -1, which means that the work done by friction is the force of friction times delta x, and there's a negative sign that's coming from the cosine. Okay, so negative work done by friction. Is the pulling force, is it doing positive or negative work? Positive, they're in the same direction. What about these two? They're not doing anything, right? They're perpendicular to the direction it's moving, so they don't do any work at all. So the answer here is negative work for the friction, pulling is doing positive, the other two are doing 0 work. So, can you think of one case, even one case, where friction does positive work? In other words, where friction is in the direction of delta x, in the direction of the displacement.
On ice, or would that be like frictionless?
On ice. Ice, we would consider it being frictionless, so it wouldn't be in the problem. So it'd be doing 0 work in that case. What about positive work? I'm giving you a hint right now, believe it or not. Do you feel the hint? I'm giving you a hint. What's my hint? Walking. Walking is my hint. My hint is walking. As I walk this way, every time my foot touches the ground, what direction is the static friction force? That way, right? All because my foot doesn't do that. Which direction am I being displaced? That way. They're in the same direction. Friction's doing positive work there to help propel me forward. So walking is one case. So our answer here is yes. I'll give you another one. By drawing you a very lovely picture. Are you ready? Let's play Pictionary for a second. You tell me what I'm drawing here. Just shout it out as you think you have answers.
You're really bad at showing.
Yes, I am. I agree. That front wheel has issues, doesn't it?
Drawing a flatbed.
It is a flatbed truck. Good job. Thank you. Truck.
It kind of looks like a sideways golf club.
A sideways golf club with a face on it. I would agree with that. It very much does. This person's not even driving. They're just going, ah! It's sad in every way. I'm sorry I can't draw, but that was fun, no? Apparently wasn't that bad. You figured out the answer pretty quick. So let's say that this is a flatbed truck with a box on the back. And let's say that now the truck goes forward, and so does the box. How come it goes with the truck?
Because it's not fastened down, and friction isn't strong enough to keep it in place.
And friction is strong enough?
Isn't.
Isn't? So if it slides off the back, friction's not strong enough to keep it in place. If it doesn't slide off the back and just stays right where it is, and the truck and the box go together, then what?
It means friction is strong enough to keep it.
In that case, friction is strong enough to keep it in place, and it must be pointing in the same direction to keep it from sliding off the back. Okay? So in that particular case, again, friction is that way, and delta x is that way. It's doing positive work. Yeah.
Wait, this was similar to a question we had on the midterm, where it's like if it slides forward, or some box slides forward or slides back. Isn't the box sliding forward? Isn't that positive work? And if it slides back, that's negative work?
If the box slides okay. So in this particular case, we're saying the truck starts from rest and then goes.
Right. That would mean the box would slide backwards. Or
If there is no friction, the box will slide backwards off the truck, or in other words, will stay exactly where it is,
depending on the strength of the friction.
depending on the strength of the friction. If it was completely zero friction, then the truck just goes and the box stays right here until the truck is gone, and then it falls. okay? If there's plenty of friction, then the truck moves and the box goes perfectly with it. If it's somewhere in between, you might imagine the truck goes, and as it gets started, maybe it slides back a little bit because it very much likes to stay in the exact same place according to Newton's first law. And then maybe friction takes over just enough to be able to keep it on the truck. Or maybe it just slides into the back, and then the back of the truck applies a force and moves it with the truck, okay? In whatever case, the box would like to stay where it is. It's only because friction points in the same direction as it moves in order to keep the box with the truck as it travels forward, all right? So 2 examples, walking and the golf club truck, both of which we have positive work being done by friction, okay? What about this one? Positive, negative, or 0? Is the catcher giving energy to the ball, taking energy from the ball, or not really doing anything to the ball? Just stopped it, but what did it have to do to stop it? Okay, let's look at this from 2 different perspectives. First of all, if it goes from 90 and it was stopped, well, clearly it took energy away. Well, that's what we call negative work. But how is that possible? Remember the superhero in the train? Does the superhero just say, train stop, and it stops? No, typically they apply a force and then get pushed some distance as they apply that force. That's probably what the catcher's doing unless they want a broken hand. It's not just like, I'm gonna catch the ball. Ow, right? It's more of a, like this, okay? So the glove goes back while applying a force against the direction of the ball in an effort to stop it. So the ball is going this way, delta x, while a force is being applied the opposite direction. That's also negative work. So you could think about that either way, a slightly more complex way, or just think about the fact that energy was taken away, so there had to be negative work done. Which brings us to this one. A ball tied to a string is whirled around in a circle. What can you say about the work being done by the tension force? Positive, negative, or 0? Negative, positive, negative, negative, positive. 0, negative, positive, yeah? Positive, we're going with positive, others are saying negative. Looking at the current situation, let's say that the ball is going around this way. What is the direction of the next little piece of displacement? Is it this way? Is it that way? Is it back this direction? Is it maybe up this direction? In that next little instant, it's going to move just a little bit that way, right? So you might imagine there's a tiny little displacement this direction as it moves that way and turns a little. What's the angle between these two? Yeah. That force isn't doing any work, okay, because it's perpendicular to the displacement. Perpendicular to the displacement doesn't do work, okay? And let's see, 2 more of these, and then we're going to talk about energy a little bit, and then we're going to be done for the day. A box is being pulled up a rough incline by a rope connected to a pulley. How many forces are doing work on the box? We're specifically talking about this red box over here to the right. And I'm going to draw out all the forces that are acting on that box. You tell me how many of them are actually doing work.
say 3.
You like 3? I like 3. Which 3?
We have tension, friction, and gravity.
These two are doing work, and there is a component of the gravitational force that's pointing back down the incline. So it's doing work as well. The normal force is perpendicular to the displacement. And let's go ahead and draw in the displacement. The displacement is that direction. So the normal force being perpendicular doesn't do any work. And then finally, notice this one is not asking about a particular force. It wants you to find all of the work done by all of the forces. Let me give you a couple of minutes to think about this one and see what you come up with. I'm going to make a couple laps around the room while you're thinking. Talk to someone around you. See if you can come up with the answer. Write things down. How's everybody doing there? Yeah? Happy? Fun? Charging? Electricity out of the room. Taking energy from the wall. Can't get work from the wall. Wonder what's under this table. There's a trap door. We should go under there and see. There's another door.
Were there any secret like underground passages when you used to work in tubs?
Not that I was aware of. If so, they were secret from me. Have you heard of secret underground
I've
passages?
heard Northwestern has.
Really?
They have steam tunnels.
Northwestern in Chicago?
Yes.
Yeah, okay. There were underground passages at Northeastern, which is in Boston. So you could avoid the snow,
Oh.
which was nice. Yeah. Most, if not all, of the buildings were connected by tunnels, which was kind of fun. Top zone. Answer a question for me. This force, the force being applied to the book by the hand, and this force, are they equal? I see some very quick nods. Let's double check that. In the y direction, notice it's moving at constant speed, so the acceleration is 0. So I've got the force being applied by the hand minus the gravitational force equals 0, so yes, they are equal. Which means that, is there a
1
question?
and 2 would be the same, wouldn't they?
1 and 2?
Yeah.
So that does mean that 1 and 2 are essentially the same answer, which means that they both must be wrong, since I can't choose multiples. So yeah, those are the same answer.
And 3 would have to be. No. Right. Is the normal force, is it like, is it the complement of the mass times gravity?
Which one, the normal force?
Yeah, the F hand. Is it, since it's equal to mass times gravity, is like one positive and the other negative?
Yeah. Yeah, I think you're thinking the right way. So let's find the work done by the hand, right? Well, it's going to be the force of the hand times whatever the displacement is. They've decided to call it delta R for whatever reason, okay? They point in the same direction, which means that for the cosine of theta, I'm going to have the cosine of 0, which is just going to be 1, and it's positive. The work that's being done by gravity is going to be m times g times delta r, and this time they point in the opposite direction, so I get a negative 1. Well, we just said that the force from the hand and the force from gravity are the same. These are equal. And delta R is the exact same thing, so those are equal. So I've got equal things, just one's positive and one's negative.
So then it
Equal
would be
amounts of
0
work.
because they cancel out.
So when I add them together, no work is being done in the book. when it's lifted at constant speed, okay? Is work being done during the instant where it's like resting and I pick it up and move it? Some work is done there. We're not talking about that part. We're talking about like, I already picked it up and now I'm just moving it at constant speed. I am doing positive work on it. Gravity is simultaneously doing negative work so that the overall amount of work being done on the book is 0. Yeah.
Okay. I probably didn't get enough sleep last night, so I'm not thinking about this right. But like, if you're lifting the book, doesn't that mean that you're applying more force upwards than gravity is applying downwards?
If you are accelerating the book, then that's true. You might remember that we said that constant velocity and 0 velocity are identical. That's essentially what's happening here. There is no difference between the two. Question?
So like, let's say you're lifting weights
Mhm.
like at the gym at a constant speed. It's gonna be like you're doing 0 work. Or
That's kind of depressing, huh? Yeah. Let's be careful about what we're saying, though. We're saying that the total work by all forces is 0. You're doing work. You took the weight, you lifted it. You did work. But at the exact same time, gravity was doing negative work. So that the total amount of work being done by all of the forces is 0. That don't mean your force was useless. Your force did work.
but to physics it was 0.
No. The total was 0, but you still did work. The thing is, the amount of work that you put in was taken back out by gravity. But that doesn't diminish your effort.
Wait, so
Okay.
gravity always has an equal opposite force to going up at a constant speed regardless of what that speed is?
Yes. If it's constant, yes, because the acceleration is 0. Okay? Let me go back to the first slide and let's think about energy here a little bit. Yeah?
So, if you wanted the work done, like, that your hand is doing on the book, is that what it would be like? Your hand times the...
The work that your hand is doing on the book would be force from your hand times how far you move it.
Okay.
So you actually are doing this amount of positive work.
Then
But
work
at
done
the
by
same
gravity-
time, gravity is doing the same amount of work. And those two things combined mean that the energy of the object doesn't change. Remember we said all the way back on the first slide that work is the transfer of energy by a force. So the book, if it has constant velocity, whatever energy it has is staying the same. It's like the kid that was over here, right? It's like, ah! If it keeps moving around with exactly the same velocity, it's not getting more energetic or less energetic. It's staying exactly the same, okay? So essentially, it's like I'm lifting the thing, applying a force, moving it, trying to put energy in, but because it's moving at a constant velocity, the amount of energy is not changing. Whatever I'm putting in is getting taken right back out by gravity, which means it's not going faster, it's not going slower, it's staying at the same level of energy. Okay? Yeah, maybe. Yes. Before we leave today, let's see. Oh, look at all those smiley faces. 09. We made it farther in the morning class. Why did that happen? We did this one and we did that one. We didn't do that one. And we did that slide. I can't do that without this. Let's stop there. That's a pretty good point. Otherwise, I'm going to be really rushed on those 2 slides to try to get them in. So, I will see you all on Tuesday. Work on your homework. You've got 2 days. Get on that. Get done with it. Do the best you can. I'm going to be lenient. It's okay. I'm going to be lenient. I can take the grades they spit out, and then I will assign my own grades. Yes.
I have a question. So at the beginning of the introduction, you said that work or joule is equivalent to
The difference is here we were asking about the total amount of work by all the forces. You're still doing a joule of work. It's just as you do that, so is gravity. It's doing a negative joule of work.
So that's how you see that.
And when you add them together, the total amount of work done on the apple is 0. But still, each force did some work. Okay? Yep, you're welcome. Yes.
There's only one problem with bad news, it's that same one.
Oh, yeah?
I kept getting stuck like 25 tries I'm on right now.
Oh, wow. Okay.
I don't know if it's the system or what, but I'm pretty sure I keep doing it right.
If you want to send me your work, you can do that, and I can review what you're doing. And
Well,
tell
I'll
you if
come
it's the
back.
system or not.
I'll come by your office today.
Okay. Congratulations on being down to 1. That's great.
Wait, I'll show you. Yep.